to kind of switch things up a little bit to allow more time to work on homework in class. That's not saying you're never going to have homework, but I'm going to try to maybe make some changes so that we are doing more in-class work, so that'll allow some extra time to answer questions and things too, since we're at a pretty good spot and we don't have to go quite as fast this semester. So that's the plan. To get us started today, I did actually print the notes handout for you. That's kind of part of my trying to get through the notes a little faster to allow you guys a little more time to work. So you're going to fill in this handout today. Some of the stuff is already, I put definitions of some things on there, but we'll kind of fill in the gaps as we go. Yes. You did not come prepared? Just like, okay, this is my Christmas present to you. Now don't lose it. It has to last you all semester.
No, I ain't got no pencil. That's the issue over there.
I literally only have one pencil. I have pens. I have
How
one
are you
pencil.
guys not prepared the first day?
All my supplies that I ordered is right here, you know, so.
I actually, hey, I got my third slate of the year. Let's see if this one doesn't get broken. My board still doesn't work, but they've ordered me a smart TV, so I will have that soon. So it's exciting.
How big's that TV gonna be?
I don't know. It's probably going to, okay, it's probably going to look ridiculous because so originally there's a chalkboard behind here. So when you take down the smartboard, you're going to see the chalkboard with a dry erase board like glued to it, because that was the first one, except it's not a real dry erase board, so it wouldn't erase. So then they bought me two small ones to put on each side so they didn't have to take down the Promethean board. So we're going to take down the Promethean board and be able to see all the layers of stuff behind it. It's going to look really nice. Okay, something to look forward to. So we are going to start talking about polynomials now and their graphs. We have already graphed one type of polynomial. We've looked at, well actually we've done a couple. We've done a lot with quadratics. We also talked a little bit about cubics when we did transformation. So those are both examples of polynomials. But we want to extend this to have some idea what the graph of an x to the fourth or x to the fifth or x to the sixth is going to look like. So that's really all we're talking about today, is just the basics of what those graphs would look like. So we're going to start off with a few definitions. And I think the easiest, instead of doing the actual like formal definition of what a polynomial is, I think I just want to put an example, a sample polynomial up here. So an example of a polynomial may be like negative 5x to the 6 plus 3x to the 4th minus x cubed plus x squared minus 3. Okay, there are lots of polynomials, but that's an example. If it is a polynomial, couple things to note. You don't have any, or you have no variables in the denominator. On my new slate, apparently I have to push really hard. So in other words, if there's a fraction, the only thing you could have on the bottom would be a number. You can't have an x on the bottom of a fraction. You can't have any variables that have a negative exponent or a fraction exponent. So what that means is all exponents have to be whole numbers. So whole numbers are like 0, 1, 2, 3, 4. So all exponents have to be nice and pretty. Okay, so those are a couple of the stipulations for something to be a polynomial. Now, some words that you might hear me use in regard to polynomials, I might ask you for the degree. If I ask for a degree, what is that? Mm-hmm. For example, in the sample I use, what would be my degree? 6. It doesn't have to be the first term. A lot of times I write them in decreasing order, but you should check. Don't just assume it's the first one. You have to look at all those terms and pick the highest exponent you see. What are the coefficients? Mm-hmm. So in this case, my exponents would be like the -5, the 3. If I say negative x cubed, what's my coefficient there? -1. X squared, its coefficient would be positive 1. Good. What's the constant? Mm-hmm. So the number without a variable. In our problem, what would be my constant? 3. What is a leading coefficient? Mm-hmm. I guess we should be careful. Here it's the first number, so it's -5. It is not necessarily the first number written. You have to find the highest degree, and it's the coefficient of that term. Okay, so the coefficient of the term with the highest degree. In our scenario, that's a -5. And finally, do you know what the leading term would be? So the leading coefficient is just the coefficient in that term with the highest power. The leading term is the entire thing. So you have to find the term with the highest power. So the highest power we saw was x to the 6th. So that whole term is -5x to the 6th. That would be our leading term. So it's just the term with the highest power. And again, that may be the first term written, but it doesn't have to be. So make sure you're looking at all of them. Alright. Any questions there? So just a couple things about polynomials. Their graph, we've seen a couple examples, x squared, x cubed. Those never had any sharp corners or breaks in the graph, and that's true for every polynomial. It's just always a nice, smooth, continuous curve. Okay, no corners, no breaks. If I ask you to do transformations, that's really not going to be something we're doing a lot of in this chapter. Very, very little, but any of the transformation rules will be the same ones that we had before. So there's no new rules there. Alright, so first thing, let's just look at some examples and see if we can identify what a polynomial is. So decide if these are a polynomial. Then if they are, we're going to tell their degree. If not, we'll tell why not. So A, would this one be a polynomial? Yes, it's a polynomial if all the exponents are whole numbers, x doesn't show up on the bottom or anything like that. So this one is yes. What's my degree? Right, doesn't have to be that first term, you just look for the highest power you see. So my degree is 4. Alright, B. No. If it's a square root, that's the same thing as a 1/2 power. So you could either recognize anytime you have a variable under a radical, it's definitely not. The reason is a radical is a fraction power. And I told you that the powers had to be whole numbers. So this one is a no. Reason, variable under a radical. Okay, C. Is that one a polynomial? No. Why? Right, we have a variable in the denominator. We have a fraction with an x on the bottom. That can't happen in a polynomial. D. It doesn't break any rules, does it? So that means it is. Okay, the degree. This is kind of a trick question. If I ask you for, if I just say f of x equals 0, can we agree that 0 would be the same thing as 0x? Or 0x squared? Or 0x cubed? Or 0x to the 4th? And I could go on forever. If it's a 0, you could really put any x you wanted with it, couldn't you? So can we say what the degree is? No, because it could be anything. So if it's just a 0, we just say it has no degree. Because you could pair x to any power with that. Okay. G of x equals 8. Is that a polynomial? Yes, it didn't break any rules. Okay, the degree. So 8. Is that the same thing as 8x? No. What would this power of x have to be? Is x to the first, is that the same thing as x? What power do you need so that x would disappear? 0. X to the 0 power becomes a 1 and goes away. So if it's a constant, your degree is 0.
Turner, yeah, Jonathan Tanner. Thank you.
Here we go. So essentially, a degree is like asking you how many variables are with it. If you're just looking at a number, how many variables do we have? None. So its degree is 0. Alright, last one. Is that a polynomial? It's written different. But do I have any negative powers, fraction powers, x on the bottom? No. It is a polynomial, it's just written in factored form. So this one is a yes. Okay, the degree. The degree is the highest power if this whole thing is multiplied out and you just have pieces added together. Now, I don't know about you, but I really have no desire to take the time to multiply this out. The other thing I just told you, a degree is like asking you how many variables are there. So if we look, this is an x cubed, so that's 3 x's. This x minus 1 is squared, so how many x's are there? 2. So if you have 3 in the first and 2 in the second, how many x's do we have all together in this problem? 5. So our degree is 5. Forgot my board. And we will be practicing that piece a lot more. So it's just like how many total variables would there be? Any questions on that? example, I would like for you to take a second and do it on your own. You can use your Chromebook if you want, or the graphing calculator on there. I just want you to draw a really rough sketch of each of these 4 graphs. So it doesn't have to be precise. I put a grid on your paper, but I don't care if you don't have any exact points. I want you to just draw me a rough sketch of them. So if you need to, use your calculator on your Chromebook, draw a rough sketch so we can discuss that. Forget anything. So what does x cubed look like? It's a chair.
Well, I'll put that in my calculator.
Alright, what does x to the 5th look like? Same thing. If we did a few exact points, really the only difference is it's skinnier. It goes up faster, but it's the same thing. What does x to the 4th look like? A parabola. How is it different than an x squared? It's just a little bit skinnier. Okay. What does x to the 6th look like? An even skinnier parabola. Okay. So if I gave you like x to the 10th, what do you think it would look like? A skinnier parabola. If I said x to the 9th, what would that look like?
When they go straight over.
Yeah, the chair, just getting skinnier and skinnier. So, what determines the shape of the graph? Whether it's an even or odd power there. Okay, so this is what we call end behavior, which is one of our main focuses for today. So if n is even, it's going to look like x squared, and if it's odd, it's going to look like x cubed. So these graphs are going to look like the ones that we have had in the past. The difference, as the power becomes larger, what happens to the graph? It gets skinnier. I'm just going to put narrows. So you're just filling in those blanks on your sheet. Okay. So the end behavior, we're going to kind of generalize this. It's what's happening as you go off forever in the positive and negative directions. Which direction are the ends pointing? And when you're looking at an entire polynomial, we looked at polynomials that only had one term. But if I said like x to the 5th plus x to the 4th plus x cubed, so on, all you have to look at is the leading term. That's what decides the entire shape of the graph. So that term with the highest power. If it is an even degree, then we've already said if it's an even power, it looks like a parabola. Now how come sometimes when we graph parabolas, they went up and sometimes they went down? What determines? Right. So if the leading coefficient is positive, it's going to look like a regular parabola. For end behavior, all I'm going to ask you to do is draw me arrows. So both ends are going up. It's up, up. If it's a negative, what would that do? Flip it. So my end behavior would be down, down. All you have to do is draw me 2 arrows going down. So about half your homework tonight is just going to be the end behavior. You're just going to look at a problem and draw me 2 arrows. Show me which directions ends are going. Now what if you got really confused and you weren't sure? How could you figure out the end behavior? Graph it. Okay, it's not very difficult to plug it in your calculator and compare if you needed to. Alright, if we have odd degree, then it looks like the cube, right? And what does the cube normally look like? The chair. So this end's going down and that end's going up. If I threw a negative coefficient in there, what would happen? It would be backwards. so it'd be up, down. So far, so good? So now we're just gonna do problems. We're gonna look at some polynomials and decide what our end behavior would be. So if I'm looking at this problem, which term would I need to look at? Okay. So my degree is 3, which means it looks like a chair. It's a positive 4, so does that change it? Nope, so my end behavior is down, up. Just a regular chair. Okay. B. My leading term, so compare all your exponents. The highest exponent is this x to the 6. So 6 is even, which means it looks like a parabola. So parabolas, both ends are going up. But I have a negative coefficient, so what would that do to it?
Down.
Flips it down, so it's down, down. Okay. C. Can I just look at this one and know my degree? We're going to have to do a little more work. I'm not going to take the time to multiply all of this out. You just need to know what your leading term would be, right? So if I'm finding my leading term, we would have a 3. It's basically picking the highest power of x and everything. This one would give me an x. Since this is squared, we would get an x squared out of that term. So if you multiply that all together, you get a 3x cubed. That's not the whole thing, but if I were foiling, that would be the term that would have the highest power of x in it. And that's the only term I need. So looking at this, my degree is odd, so it's looking like a chair. I have a positive 3 in front, so does that change anything? No. Nope. So it's down, up. If you needed to check yourself, you can plug that entire thing into your graphing calculator and graph it to check. Let's do another one where we would have to think about multiplying it out. Okay, so this is one really ugly. If I told you to FOIL this whole thing out, it's going to take you the rest of the class period and probably then some. Right? There's a lot of stuff here. But I don't need everything. I just need the leading term. So I have the 1/2. This parenthesis, the highest power of x is just an x squared. And this parenthesis, if you have an x squared cubed, what do you do with those powers? Multiply. So that would give me an x to the 6. And the last one, I have an x to the 4. Right? When you multiply this together, what do you do with those exponents? Add them. So 2 plus 6 plus 4 is 12. That's all I need. 12 is even, so it's like a parabola. 1/2 is positive, so it doesn't flip, so it's up, up. Any questions there? I would like for you guys to do the next example on your own. I've given you 4 equations and 4 graphs. Just using the end behavior, I want you to match which is which. So, the first graph is an x, or the first equation is x to the 4. So its end behavior should be up, up. So that's graph C. Or some of you labeled down here, C would be the f of x equation. Alright, G. That one has a negative x to the 6. So 6 means even, looks like a parabola, but the negative would flip it upside down. So that one is A. Okay, 3x cubed, what does that look like? A chair, so that is B. And negative 7x to the 7th, what's that? Backwards chair, so that is D. Is that okay with everyone? Okay. I'm gonna go for just a few more minutes. Just want to get through a few more terms, and then we'll stop for today. So turning point is where a graph changes direction. Okay, in other words, if I have a graph like this, my turning points are right here and right here, because I was going up and I switched and went down. I was going down and I switched and went up. Turning points, another word for those are extrema. In other words, they're maximums and minimums. They're high and low points in our graph. So if I ask you to find the extrema, those are just maxes and mins. An absolute max or min means the overall highest or lowest point on your graph. In other words, let's say I gave you this graph. Does it have an absolute max? Yeah, the single highest point on the graph is right there. Does it have an absolute min? No, because these ends are going down forever, you don't have a single lowest point on your graph. Okay, local maxes and mins don't have to be the highest or lowest on the graph. They're just higher or lower than the points surrounding them. If I'm looking at this little picture that I drew, how many local minimums would this graph have? Points that are lower than the ones surrounding it. Just one. This right here. It's not the lowest point on the graph, it's not an absolute, but it is a local because it's lower than the points surrounding it. Local maxes, there are two. This absolute max is also a local max because it's higher than the ones around it. This point here is also higher than the ones surrounding it. Do you guys see that? Okay, so you can have multiple local maxes and mins. Let's do an example of that, and then I think we'll probably be ready to stop. So here's the graph that I put on your paper. Local extreme points. So I want the local max and the local mins. You can list these a few different ways. You can give me an ordered pair if you want. Technically, all you have to do is give me the y value I don't care, so you can either give me the full order pair or just the Y. So local maxes. In the first graph, what would be a local max? A point higher than the ones around it. CD. Or you could just say D if you didn't want to give a full order pair. What about the second graph? What's higher than the points around it? MN. Local min. So lower than the points around it. In the first graph, what would that be? B and H. And again, you could list the order pairs AB and EH. I'll just list the Y's to show you the two different ways you could write it. What about in the second graph? Just K. Or if you were listing order pairs, you do the JK. Oh, I did both of them together, didn't I? Okay, the first one I asked for F, second one I asked for G. We just did both of them, so I'm going to skip to the third question. The absolute extreme points for F and G. So I need the absolute max and the absolute min for each graph. They may not have one. It's not a requirement. So looking at F, does it have an absolute max, a point that is higher than everything else? No, because both ends are going up. Does it have an absolute min? Yes. Where? EH. This is the lowest point on the entire graph. Okay, if I'm looking at G, does it have an absolute max? No, this is my only max, but that end keeps going up, so it doesn't have one. Does it have an absolute min? No, because that end keeps going down. So we have no maxes on it. Is that alright? I'm just going to mention one more thing and then give you time to do your homework. It's a very quick handout, so you'll probably get done. The last thing I want to mention, and I'll pick up here tomorrow, there is a relationship between the degree and the turning points. If you have a degree of n, you have n minus 1 turning points. In other words, if my degree is 7, my graph can only change directions 6 times. If my degree is 3, how many times could it change direction? 2. If it was 10, it could change direction 9 times. Likewise, if you're looking at a graph, you can tell what its degree would have to be from that. If I gave you, let's say, this picture. How many turning points does this have? It has 4, so my degree would have to be 5, because the degree is 1 higher than your turning point. Okay, so since I have 4 turning points, my degree would have to be at least 5. Alright, is that okay? So we'll pick up there tomorrow. Your homework tonight, there is a handout posted on Classroom. I don't want you to do the last 2 questions yet. We're going to do those at the beginning of class tomorrow together.